Hiya! Another biology with Miss Cherry, and today we're getting straight into it. No starter because it's a big one. So this is 40 lessons, no, 40 slides, not 40 lessons, on the cardiac cycle. It's quite meaty. There's quite a few diagrams involved, so we're going to take it slowly, and I'll direct you to any extra resources that you might need that I've put on OneNote throughout the lesson. You're going to have to be patient. It's going to take a little bit of time. If you don't understand anything, I really need you to let me know as well throughout this lesson. So let's get started. Now, the cardiac cycle is what we call the whole idea of blood moving into the heart and then being pushed out. And we call those two separate stages the filling stage and the ejection stage. So obviously filling is where blood's coming in, ejection is where blood is leaving. And now we know that the heart is myogenic. We covered that last lesson, but what you might not know is that it's actually electrical impulses that come from your brain down your vagus nerve, so alongside your neck, and into the heart muscle itself at various regions called nodes that cause the muscle to contract. So the heart contracts from the top down, so it squeezes at the atria and then squeezes up from the ventricle in a kind of rhythmical motion. And that motion, that rhythmical pump from the top, pump from the bottom, pump from the top, pump from the bottom, gives us three main stages of the cardiac cycle that we can recognise through blood flow, through pressure changes, and through the movement of blood around the tissue itself. Now, these three stages are at the bottom. There are a few different ways to say them, so I'll give you the options. I don't mind which way you say them as long as you can spell them in the exam. So you've got atrial systole or atrial systole, ventricular systole or ventricular systole, and diastole. Some people say diastole as well, but I don't particularly like that one. I think it sounds ugly when the word is quite simple. Now, things to be aware of is that systole or systole are periods of contraction, so parts of the heart muscle are going to be squeezing, whereas diastole is very much a relaxation phase, a kind of release from all of the tension that's built up in the heart. So we're going to take each of those stages in turn. We're going to start off with the relaxation phase because this is quite a passive flow of blood. Now, on the left-hand side of the screen, you can see that we've got the standard slide, but on the right-hand side of the screen, I've done some horrible little heart pictures that I'm going to be using throughout the next few slides to explain. I prefer the little diagrams that I've drawn just because it's easier for me to show you where things are happening. But if you don't like them, completely ignore them. If you do like them, you're welcome to draw. The third thing we've got to remember is that throughout this cardiac cycle, we're talking about blood flowing in through both sides of the heart. So this is not like left-hand side goes first, right-hand side goes second. It's a double circulatory system, so things are happening at the same time. So as you can see, we've got the right atrium. Oh, that pen is too big. On the right hand side, and the left atrium on the left hand side, and then the left ventricle and the right ventricle. And notice that I've drawn in that left ventricle with a thicker wall just so we can remind ourselves that it's got that big muscle there ready to increase the pressure, because it's not quite as visible on the diagram. So we know that blood is going to return to the heart through either the vena cava or through those pulmonary veins. Okay, so if you didn't know that, maybe go back to last lesson and double check the anatomy of the heart. But we are looking at the vena cava or the pulmonary veins. Okay, so on my first diagram, my blood is coming in to the atria. And what that's going to do is that's going to start to stretch my atria. So instead of blood just sitting there passively, remember this is a muscle. So that blood filling in the space is going to start forcing the tissue outwards and almost bulging the sides of those atria. And now I've made a little bit of a boo-boo on my diagram before we move on, because all of these valves should actually be closed. Okay, there's no reason why they're open. So the valves are just those bits that are dividing the atrium and the ventricle. So remember, we've got the atrioventricular valves, and then we've got the semilunar valves or the bicuspid and tricuspid valves that separate the ventricles with the vessels leaving the heart. So those atria are going to fill, a bit like if you try and take loads of water into your mouth at the same time. You've got that pressure on your cheeks, and the pressure in the atrial walls are going to increase as well. And eventually, the pressure in the atria is going to exceed the pressure of the ventricles. So remember, blood is going to be pushing, and we're still looking at that top diagram, guys. Blood is going to be pushing on those valve walls, valve flaps, if you like. And eventually, those atrioventricular valves are going to open. So I'm going to move down to the next diagram. So we can see now that the valves are open. And now what that means is that our blood is just going to be able to flow. So it was initially contained all up in the atria, and instead now it's able to drop down because of gravity. No contractions here. We're not in systole, we're relaxed in diastole to the bottom of our ventricles. Okay, this is a passive movement. All we're doing is getting blood into the heart, and we're getting a change in pressure. And what that means is that over time, the ventricles are going to passively fill with blood. So not all of the blood has escaped the atria at this point. There's still some blood in there, but by the end of diastole, we have got the atrioventricular valves open. So we'll move to that bottom diagram now. We've got the atrioventricular valves open, and we've got blood passively passing into the ventricles. Okay, not all of the blood, but some of the blood. This is a relaxed state, not active, no contractions whatsoever. But we are going to move into atrial systole next, or atrial systole, which is where the contractions actually begin. So now we know that we started with some blood in the bottom of our ventricles, that passive flow from the end of diastole. And we know that all of our valves, so our semilunar valves, are closed, but our atrioventricular valves are open. And the first part of atrial systole, which is really, really important, is that the wave of excitation, that electrical impulse that passes through the heart tissue, causes the atria to contract. Okay, so a bit like a big pinchy squeeze from the top down, and that's what those green arrows are, of those atrial walls. Now what that does is it releases and forces all of that blood out of the atria into the ventricles, which are still really relaxed. There's no contraction there. So now I'm going to draw a little dot, dot, dot. All the blood has exited the atria and is now in the ventricles. But as I said, nothing's going on in those ventricles. They are completely chill. Nothing at all. Now we've got no blood in our atria, or very, very little blood in our atria because it's all been squeezed out. Lots of blood in the ventricles, and we're ready to try and get that blood out of the heart. And then finally, we are onto ventricular systole. So we've got our ventricles nicely filled with blood that's been forced into there by the contraction of the atria. So now, and the ventricular walls are going to start their ventricular systole phase by contracting. So we get a squeeze inwards now from the base of the heart up. So we call the bottom bit of the heart the apex. Okay, the apex generally just means a point. So you can have the apex of a triangle is just the point where things meet. But the contraction starts from the apex of the heart upwards. And what that does, if both of those ventricles contract simultaneously, is it forces the blood upwards back towards those atrioventricular valves. Okay, so we've previously said that the atrioventricular valves are open, but now if we move into the second picture, the blood is actually being moved back and working against them. So I recognise that this diagram isn't very accurate, but the green shows the movement of the blood. And what that does is it shuts the atrioventricular valves. It stops the blood going backwards. But because we've got our semilunar valves and our atrioventricular valves closed, we've now got an increase in pressure. So the space available for that blood to move is slowly going to rise as the ventricles carry on contracting. So you can see in the diagram now what I'm doing is I'm filling up the space with all of that blood, the blue pen. And eventually what happens is that the pressure in the ventricles exceeds the pressure found in either the pulmonary arteries or the aorta. So that blood now is going to be able to be released. So it's forced all the way up and it can move out of the vessels and go to its either systemic circulation or pulmonary circulation, depending on where it's going. So we've got a relaxed heart, dropping down of the blood from the atria to the ventricles due to gravity, contraction of the atria, squeezing the blood downwards into the ventricles, but the ventricles are still relaxed, they just take it and expand a little bit. The ventricles contract from the base up, a bit like squeezing a frube, forcing all of the blood back up towards the atrioventricular valves, which forces those closed, and out of the semilunar valves because they're forced open by the change in pressure. That is one cardiac cycle. Now, unfortunately, with the cardiac cycle comes this horrible diagram. Now, if you look on OneNote now, there's a file called Wigger's diagram, and I'll write it up there for you as well so you don't think I'm saying anything horrible. Wigger's diagram shows the pressure and the volume of different chambers and vessels of the heart at various points in the cardiac cycle. So you can see that they've labelled in systole and they've labelled in diastole regions for you. So systole is pink, diastole is purple, and they've also given you some key events, so what's happening at each stage. Now we're going to take a few of these and go through them together so you can label it on your diagram, and then you guys are going to do the volume change one for me at the end. So we're going to start by looking at the ventricular pressure, that red line. And if you wanted to, maybe you are super cool and technical, unlike me, you might want to use like a dropper tool and perhaps colour over the other lines so that it means that you're only focusing on that red one. A bit like what I've done there. Oh, look at me go. I'm such a tech whiz. So we're looking at the beginning at a diastole phase. And if you're drawing on your own version of the diagram, it might be worthwhile labelling that at this beginning region, we're still relaxed. So in the diastole phase, the ventricular pressure is low. We know that. It's relaxed. It's not doing anything. But over time, so over the period of diastole, the pressure is going to rise. And that's because we've almost got the atria not necessarily contracting, but almost recoiling as it fills with blood. So the atria fill and then the elastic walls of the heart sort of bounce back and force that blood down a little bit. It's the movement of gravity that we're talking about. So over time, we can see that the ventricles have a little increase just while the atria fill and we get that passive movement of blood from the atria down to the ventricles because of gravity. But then we move into the systole phase, the atrial systole and then the ventricular systole phases, and we get that massive increase in pressure. And you might want to pause now and consider why that large increase in pressure occurs. Remember, we're still only talking about the ventricles. And that's because we've got the atrial systole and then the ventricular systole. And in both of those phases, so in atrial systole, we have got blood being forced into ventricles, which is going to cause strain into them. But then, when we've got ventricular systole, we've got that ventricular contraction which closes all the valves. And that means we're going to get that rapid increase in pressure up to the peak of that red line, after which the semilunar valves open. And after those semilunar valves open, the blood is able to flow out and we get a nice relaxed diastole phase again, where it's just passively flowing into the heart. Okay, the pressure is going to drop again back to that baseline level, but notice ever so slightly in that diastole section, the pressure is gradually increasing. It slowly increases as the blood drops from the atria back into those ventricles again. If you missed any of that, pause the video, rewind, go over it again and pause to the bits. I was going through different slides with the text that stayed the same. But so there were different notes on different slides that you might have missed. The next one we're going to have a look at is the dotted line, the atrial pressure. So the pressure of the atrium, the chambers at the top of the heart. And you can see here that for the most part, the pressure in the atria is always similar or lower than that in the ventricles. So at the beginning of the atrial cardiac cycle-ness, we have got a slight increase in atrial pressure during diastole. Okay, and like I said when we were looking at the ventricular pressure, this is because the atrial walls are going to fill with blood and then they are going to recoil. Okay, and again, where step 2 is as well, we've got the contraction of the atrial walls, which again is going to force blood out of those chambers and into the rest of the cardiac system, so down into the ventricles. Now again, we've got a pressure drop after that contraction phase, so contraction where number 2 is. We get a recoil, a bit like the atria going, oh, okay, I've contracted now, I'm just going to relax. And at that phase, or that stage, we get a temporary increase in atrial volume. So a bit like if you do a big stretch and then relax, your body feels a little bit more loose. That's exactly what happens with the atria. So they give a big squeeze and then they go, oh, okay. And they get slightly bigger just for a second. And then over time, as we steadily refill the atria again, so over the end of ventricular systole, remember blood is still going to be coming in through the vena cava and through the pulmonary veins. Over time, the volume of blood in the atria is going to continue increasing, and eventually we are going to reach that increased pressure again, ready for blood to leave, drop down through gravity, back into the ventricles. Now the final one that we're going to look at is the aortic pressure. And the aortic pressure is really, really, really high, much higher than any other chamber of the heart. Remember, the aorta is a vessel, and it's the major vessel leaving the heart muscle itself to go back to the body. And the aortic pressure sort of maps very similarly the ventricular pressure. And you can see the arch of the curves for both the green dotted line and the red line sort of follow on, but there's a very small gap between the pressure changes, and we're going to have a look at that in a second. So we've got that high pressure initially just as a baseline standard because the walls of our aorta are really, really thick. They're highly elasticated. There's a lot of recoil and stretch going on. And at the same time, they've got a small lumen. So all of the blood passing through them, there's loads of blood leaving the heart every time it beats. All of that blood is fit through a really, really small hole. If you're not too sure about what difference a small lumen makes, think about drinking a McDonald's milkshake with those horrible rubbish, teeny tiny thin straws. It's a nightmare, you get a headache all the time. Versus a KFC Crush'ems, which has got quite a big chunky straw. It's a lot easier to drink that way. There's less resistance the bigger the lumen. Now, over the contraction of the atria and then the ventricles, we can see we get that increased pressure, especially in the aorta, and this is because the chambers themselves are going to put pressure on the aorta. So the heart itself isn't very big. It's confined to a small space. So if you think about the structure of the heart, it's like that diagram that we've looked at over the past few slides. If my atria over here start getting bigger, that's going to start squeezing on my aorta, which is only there. Yeah, comparatively, where one space fills up, so the aorta fills up and then the ventricles fill up, that's going to take space away from other vessels and tissues surrounding it. There's a finite amount of space there. But once we've got the semilunar valves open, we've got that release of blood from the ventricles, again, that's going to start releasing the pressure out of the aorta because blood is able to just flow away, and we get that, again, relax, recoil phase where the aorta itself can sort of go, again. Now it's your turn. Have a go at using your knowledge of the cardiac cycle to explain the changes in the ventricular volume over the course of one cardiac cycle. So you could draw the diagram in your books if you want to, or you can label it straight onto the picture if you've printed it out. And go for it. Give yourself about 5 minutes, look back through all of your notes, and then play again when you're ready to go through the answers. So the first bit we've got is a period of increased ventricular volume. So the blood is starting to fill. I'm going to cross out atrial there because that shouldn't really be there. And the initial increase when atria contract, we're talking about the recoil again. So that blood is being dropped from the atria down to the ventricles in the relaxed phase. Now after atrial contraction, so atrial systole, the amount of blood in the ventricles is going to stay the same. Okay, and that's why we've got that slight plateau. However, the ventricular volume is going to drop when the semilunar valves open. And in this case, we can see that it goes from around 120 millilitres all the way down to 40 millilitres over about 0.2 seconds. Okay, and it's at this point that all of the blood has been ejected from the ventricles and they're completely empty. Then, over the diastole period, as the ventricles are going to passively refill, so again, from the atria dropping down into the ventricles because of gravity, we get a slow, passive increase in ventricular volume back to that starting level of about 100-110 millilitres. And here we've got an exam hint just to keep you focused on the relationship between pressure and volume. They're inversely related, so when one increases, the other decreases. For example, if I had 10 millilitres of fluid in a closed egg cup, for example, so I put a lid on an egg cup, that's going to have a higher pressure if I shake it all around than if I put 10 millilitres of water in a big mixing bowl to make a cake in. Okay? Pressure and volume, when pressure increases, volume decreases, and when volume increases, pressure decreases. Now I'd like you guys to have a look in your books just for a little break for me so I don't have to carry on talking. I'm joking, it's like I'm in front of you, but I'm not. Spend a few minutes having a look at the pages in the book related to this chapter and how valves control the flow of blood through the vessels and the heart. So looking at the roles of the bicuspid and tricuspid and semilunar valves. I'm not going to be covering it, so if you don't do it, you're just at a bit of a loss, aren't you? Now, we've covered cardiac volume before, and we've had a look at it previously. We've done this equation. We know about the stroke volume and the heart rate. But as a definition, it's a measure of the volume pumped out of one ventricle of the heart in 1 minute. And we just previously looked at it as a measure of the blood pumped out of the heart in 1 minute. But the one ventricle is really important because we're using a left ventricle, the highest pressure possible, and we're looking at how it moves through the systemic circulation. So please make a note of that equation. Cardiac output in decimeter cubed per minute, you can write it in that way as well, is equal to the stroke volume in dm cubed per beat times the heart rate in beats per minute. And the reason I'm asking you to do that is because we're going to have a look at these exam questions, and cardiac output comes in various different forms, looking at these calculations. So here we've got a table showing the volume of blood in a woman's left ventricle at different times during 1 second. Use the data in the table to calculate her heart rate in beats per minute. Now you can pause and have a go and let me know what you get. So you're working out her heart rate in beats per minute. And then the stroke volume is the volume of blood pumped out of the left ventricle during one cardiac cycle. Use the table above to determine the stroke volume. Again, have a go. Play again when you're ready. Now here are the answers. So you should have got 66.7 beats per minute and a stroke volume of 70 millilitres. If you did, that's great. You can skip probably a couple of minutes ahead. But if you didn't get that, I'm going to show you where this information comes from those tables. So use the data in the table to calculate the heart rate in beats per minute. So I'm going to look at the time down in this left-hand column, and I'm looking at the volume of blood in the left ventricle. And I can use my knowledge that the volume in the left ventricle should be the same at the start of every cardiac cycle. So I'm going to look down and see where I see 112 centimetres cubed again. And it's not until I get down to 0.9 seconds that my ventricles have the same volume as they did at the very beginning. So I know that one cycle takes 0.9 seconds, and there's 60 seconds in a minute. So 60 divided by 0.9 should tell me how many cycles I can get in that 1 minute. And I'm just going to pause for a second, do it on a calculator, and then I'll be back. She's back, which gives us 66.66 reoccurring cycles, but to one decimal place, 66.7 as required. So that is my heart rate in beats per minute. Now for the stroke volume, it tells us it's the volume of blood pumped out of the left ventricle during one cardiac cycle. And I know that I'm going to be looking from 0 to 0.9 seconds because that's where we've said that it cycles round from 112 millilitres all the way back round to 112 millilitres after being ejected and then refilled. But in that time, I'm looking for the range of values. Okay, so remember, I'm looking for the highest, which is 120 millilitres, to the lowest, which is 50 millilitres, and that is actually how much blood I have pumped out in one cycle. Please don't get it mixed up or confused. It's not the start minus the lowest, it's the highest to the lowest volume that is present in the heart, and that is the 70 millilitres that it required. Now here's another one. When a stethoscope is placed on the chest wall, sounds are heard as the heart beats. These heart sounds are caused by the valve shutting. The diagram shows the heart sounds from resting. In this person, the stroke volume is 70 centimetres cubed. Calculate the cardiac output and show your workings. So you've been shown there the stroke volume, and you've got a repeating pattern of valves opening and closing. So to calculate the cardiac output, you first need to work out the heart rate and then use your equation. Pause now and have a go, and again I will show you afterwards. So here we've got the answers again. You should have got the cardiac output of 5250 centimetres cubed per minute. If you didn't, you could have got 1 mark for saying that the heartbeat is a 0.8 second duration, that the heart rate is therefore 75 beats per minute, or writing the equation cardiac output is stroke volume times heart rate. If you weren't too sure though, I'm going to go on to the next slide and I'm going to show you how to get those values and then how to use them together to get the equation or to get the answer right. So I told you previously that this is a rhythmical cycling of the same pattern, and they've helpfully labelled the valves A and B. Now, I'm going to presume that from A to A, that is one heartbeat. Okay, so when a valve closes and then it's got time to open and then it closes again, those sounds that I can hear mean that the heart is beating separate times. So I'm going to say that the duration between A's is equivalent to the length of a beat. And you can pick B's if you fancied. I'm going to go for A's because they seem to line up a little bit nicer with the markings on the scale at the bottom. Now I can see that there between 0 and 1 second, there are 5 separate sections, which means that each of those sections is worth 0.2 seconds. Okay, so between this first A, which starts at 0.2 seconds, and this second A, which ends at 1.0 seconds, that duration of A to A is 0.8 seconds. And you can check that again between the next two A's, so this is 1.0 across to 1.8 seconds, and then 1.8 to 2.6 seconds again as well. Okay, so if each of my beats is 0.8 seconds, we do exactly the same as the previous question. So the heart rate is 60 divided by 0.8, which gives us a heart rate of 75 beats per minute. Okay, now that's not the entire answer. Remember, we've got to figure out the cardiac output. So the cardiac output is heart rate times stroke volume. And this is why I underline all of the values in my question, because I know that it tells me that my stroke volume is 70 and my heart rate that I've just figured out is 75. So if you multiply those two values together, it should give you the 5250 that the mark scheme required. Now that previous question relied on a pattern of waves that you might not have seen before, but if you enjoy a medical drama you might have seen, and that's an ECG. And an ECG is a rhythmic repeating pattern that looks very much like that diagram, caused by electrodes being placed at different points on the body to give that shape. And the shape is made because of the waves of electrical activity through the heart. Generally, we've got a P wave at the beginning, followed by a QRS segment in the middle, that big drop, peak, drop, and then a T wave at the end. And if that repeats, and it's normal and it's pretty standard across in duration and shape and height and things like that, then that's fine. But sometimes medical conditions can cause variations in the ECG trace, and you have to be able to recognise them. Now, this is not to say that you guys need to be a doctor or anything like that. You just need to be able to recognise too fast and too slow and a couple of abnormalities. So at the top, we have got a normal ECG trace. Okay, you can see each heartbeat from P wave to P wave is about a second long, and normally they're quite good in giving you a scale that you can see there. Now, the normal heart rate is about 60 beats per minute, so you would expect to see a beat every second or so. However, if you've got a slightly slower heart rate, the beats are going to be more spaced out, so you can identify that by comparing where the P waves are. Okay, so remember, the P waves are that first little lump. So from P wave to P wave, now you can see compared to normal in bradycardia or bradycardia, that slowed heart rate means that the P waves are spaced apart even further. Now if we carry on down to tachycardia, which is a fast heart rate normally seen in people that are stressed or anxious or having a panic attack, that P wave is now a lot closer together. Okay, so remember, the P waves are the bits that I'm circling in blue, they're not the point. You can use the point-to-point measurement as well, that's the QRS complex, but I just like using P because it's the first bit. An ectopic beat is where you've got a bit of a funky system going on. So you can see here that we've got extra beats going in there. So we've got maybe an extra systole section where maybe there's slightly too much contraction, so too much blood is ejected. Hence we get a rapid drop or change in electric activity. And then there's a pause. Okay, and ectopic beats are defined by that small pause between the beats when nothing's happening. Slightly problematic if nothing's happening in your heart, implies that something's gone wrong. And then finally, we've got atrial fibrillation, and that's just a completely irregular rhythm. So you've still got the QRS peaks, so you've still got those points in the graphs, but everything else between it is an absolute mess. And this is a bit like where your heart is spasming. Yeah, if you imagine like trying to open and close your hands as quickly as possible, that's kind of what the heart is doing. It's not really working to its full effect. And again, you don't need to be able to say, oh, this person's tachycardic and it's got this condition. You just need to be able to recognise that tachycardia is a fast heart rate. So we're going to have a go at a few more exam questions, but these are very much test yourselves. Okay, so the graph shows the volume changes in the left ventricle of a human heart during 2 cardiac cycles. Numbers 1, 2, 3 and 4 represent times when heart valves open or close. Use the information from the graph to complete the table in part A and place numbers 1, 2, 3 or 4 in the appropriate box. You only need to use each number once. You should only use each number once, so that's not a trick. There's no number 2s that are involved in there. Have a go. 2 minutes. Spend about 3 minutes considering it. Maybe have a look and think about what's happening at each stage of that ventricular volume cycle, and then play again when you're ready. Question 2. Use the diagram above to calculate the volume of blood pumped per minute by the left ventricle. Again, 2 marks. Pause and play again. You're working out the cardiac output. This is what your answers should look like. So the table at the top. If you're not too sure about the answers, please pop up and let me know, and I will help you go through it and I'll explain what's happening. And then for the cardiac output, you should have got an answer between 6,315.79 and 6,400, but you could have got a mark for saying that the stroke volume is 80 centimetres cubed, or using that equation. You could have said that the length of a beat, the heartbeat duration is 0.76 seconds, and therefore the heart rate is 79 or 80 beats per minute. And there's a range of answers you could get here, so check that yours lies in between them. And if it doesn't, maybe you need to look at a graph more effectively or clearer. Maybe you just need to work on your rounding skills. And these are the last few questions. The human heart has 4 chambers. In which one of the 4 chambers does pressure reach the highest value? And then explain how the structure of this chamber causes the high pressure. It's only 2 marks, shouldn't take you too long. Now the next question, the table shows the volume of blood in a man's right ventricle at different times during one cardiac cycle. Use the data to calculate his heart rate and then his cardiac output. We've done a question like this already. You can do it. It should take you a few minutes, so pause and play again when you are ready. And the final one. Use the information from the table below to show whether the valves are open or closed at each of the times shown. Okay, write open or closed in the appropriate boxes. So this is the volume of blood in the right ventricle now. We're not talking about the left anymore. And that's trying to trip you up, but it shouldn't do. It's exactly the same as the other side. Remember, the 2 cycles happen concurrently. So pause, think logically, and play again when you're ready. Now the final slides are for the marks. So here we go. We've got the left ventricle where the pressure is the highest. The thickest muscle is there, or that it's more muscular, or that there's thicker walls. But the muscle is not stronger. There's just more of it. The heart rate of that person from the table was 85.7 or 86 beats per minute. It says accept 85. But ignore additional decimal places. I don't know what the actual answer is, but if it was like 85.77776, just ignore them. You would have got 2 marks for the cardiac output of 7905 to 7998, so you've got about a 90 centimetres cubed per minute difference. But if you've shown evidence of doing heart rate times stroke volume, there's a mark there. And here we've got the answers to that table, so it should have been closed, open for 1 mark, open, closed for the other. And that is us done. I know it's been a difficult lesson. It's been really challenging. It's been tiring for me. I've been doing it for about an hour and I'm only talking to you. I'm not even asking you guys questions in front of me. Thank you so much for bearing with me. If you do have any questions, please ask. I'm happy to go to a breakout room and explain things with you. I'm happy to show you how to do the answers. I just need to know. All right, see you again next time, guys. Have a lovely day. Bye.